Hey everyone, and welcome back to The Explainer. I am super excited to have you here today. Okay, let's dive right into this. Today we're decoding a really fascinating engineering lesson, pulling directly from the AMTE 113 lesson on aircraft structures. Our goal is to take what is essentially a highly technical, complex framework for flight controls and translate it into a clear, visual blueprint of flight that just makes sense. We're going to make the complex world of aerodynamics incredibly accessible. So, I want you to start by just picturing this. You're up in the air. How do you actually steer a machine through the invisible geometry of the sky? It's kind of a wild thought, right? Because unlike a car that turns by physically gripping asphalt, an airplane maneuvers by pushing against the air itself. For the next few minutes, I want you to step into the shoes of an aircraft designer, or maybe a student pilot. Imagine you're in a metal tube with wings. How do you actually command it to dance in 3 dimensions?
Here is our game plan for today. First, we'll map out the 3 axes of flight. Then, we'll look at the primary flight controls. And finally, we'll dive into the auxiliary flight controls.
All right, part 1, the 3 axes of flight, defining the geometry.
Before we can even think about installing a steering wheel or a control stick, we absolutely have to define the 3-dimensional space that the aircraft is operating in. We have to map the invisible lines of rotation. Think about a single point right in the middle of the plane. That is the center of gravity, or the CG. Every single rotation an aircraft makes, no matter how extreme the maneuver is, happens precisely around this exact intersecting point. It's basically the fulcrum for the entire machine up in the sky.
Let's break those invisible lines down, starting with the lateral axis, which you'll sometimes hear called the y-axis. Imagine a giant, invisible pole extending straight through the aircraft from one wingtip to the other, passing right through that center of gravity. Rotation around this specific line is called pitch, so when an airplane points its nose up towards the clouds or dips it down towards the ground, it is pitching around this lateral axis.
Next up, we've got a line running lengthwise from the very tip of the nose all the way straight back through the tail. This is the longitudinal axis, or the x-axis. Movement around this one, that's known as roll. If you've ever watched an airplane dip one wing low and raise the other one up to start a turn, yep, you were watching it roll right around its longitudinal axis. And finally, to complete our invisible geometry, we have the vertical axis, the z-axis. Picture an imaginary line passing straight down vertically through the center of gravity. When the plane rotates around this axis, it's called yaw. Think of a car skidding on ice, where the nose slides to the left or the right while it's still moving forward. That's yawing. The big takeaway here is that by mastering pitch, roll, and yaw, a pilot gets complete, absolute command over the aircraft's attitude in the sky.
Moving right along to part 2, primary flight controls, installing the steering.
Okay, so we've got our invisible lines mapped out. Now it's time to add the actual physical hardware. This is where we shift from theoretical axes to the tangible stick and rudder mechanisms that pilots actually get their hands on. Flight controls are basically carved up into 3 main groups: primary, secondary, and auxiliary. And honestly, it's pretty fascinating. Even engine controls are technically considered flight controls. Why? Because changing your thrust directly changes your speed, which completely alters how the aircraft flies. But for our aerodynamic surfaces, we stick to these 3 groups.
Let's zoom in on the primary controls. By definition, these are your absolutely essential, non-negotiable aerodynamic surfaces. We're talking mainly about the ailerons, the elevator, and the rudder. These are the tools a pilot relies on constantly, making these tiny, continuous micro-adjustments to safely command the plane's direction during flight and even while taxiing on the ground. Without them, you're basically just a passenger in a metal glider.
To see how this actually plays out, let's look at the elevator. The elevator sits right on the back edge of the horizontal tail section, and it gives the pilot a direct cause and effect loop. When they pull the control stick backward in the cockpit, physical linkages move the elevator surfaces up. That pushes the tail down, which in turn forces the nose to pitch up along that lateral axis we talked about earlier. It is just beautifully simple mechanical leverage happening at 500 miles per hour.
All right, part 3, auxiliary flight controls, taming low speeds.
Now, flying isn't just about blasting through the sky at top speed. Eventually, every plane has to come back down. And here is the massive challenge. A wing built to cruise efficiently at 600 miles per hour is absolutely terrible at producing lift at 150 miles per hour. So how on earth do we keep a heavy jet flying when it slows down to land? The secret is auxiliary controls, specifically flaps and high lift devices. Their whole elegant purpose is to temporarily reshape the wing. By extending flaps, we physically increase the camber, which is really just the curve of the wing. That artificially bumps up the lift coefficient, meaning the wing can suddenly generate huge amounts of lift at much slower speeds, safely lowering the aircraft's stall speed for landing. We are essentially morphing the wing mid-flight. And aerodynamicists have come up with some brilliant variations to maximize this effect. You've got Kruger flaps, which actually extend out from the leading edge or the front of the wing on high-speed jets. Then there are Fowler flaps, which are super cool because they slide backward before they hinge down, so they don't just add curve, they increase the total surface area of the wing itself. And there are even blown flaps, which actively blow engine air right over the wing to cheat physics and create even more lift. But honestly, the sheer ingenuity of the slotted flap is amazing. See, when a standard flap hinges down really steeply, the air flowing over the top tends to detach. It gets turbulent, you lose lift, and you stall. A slotted flap fixes this by leaving a perfectly calculated gap, or a slot, right between the wing and the flap. That gap acts like a high-speed nozzle. It takes high-pressure air from underneath the wing and shoots it right over the top of the flap. That fresh blast of air re-energizes the boundary layer, keeps the airflow hugging the flap cleanly, and drastically delays a dangerous stall. It's an absolute masterpiece of fluid dynamics. To bring this abstract aerodynamic stuff back to reality, let's talk about the leading edge cuff. This is an auxiliary high-lift device that physically droops the front section of the wing downwards. You'll see these either factory installed or even added on later as aftermarket mods for smaller fixed-wing planes. Now, you might be wondering, why would we want the wing to droop? Well, when an aircraft is flying really slow and its nose is pointed high in the air, which we call a high angle of attack, the air really struggles to climb over the blunt front edge of the wing. That physical droop acts as a critical safety net. It rounds out the front, catching the air and basically forcing it to attach better to the upper surface. Just like flaps, this effectively lowers the stall speed, making sure the plane stays flying safely when it's slow and maneuvering close to the ground. So we've built an incredible blueprint today. We went from the invisible axes of pitch, roll, and yaw, through the primary control sticks and elevators, all the way to those shape-shifting auxiliary flaps that help us tame our landings. But as we wrap up this explainer, I want to leave you with a provocative thought. Aviation is literally always evolving. As aircraft keep pushing the boundaries of extreme speed, autonomous flight, and unprecedented fuel efficiency, what will the flight controls of tomorrow look like? Are we even going to use physical flaps, or will we find new ways to warp the air itself? Thank you so much for hanging out with me on this deep dive. Keep learning, keep exploring, and I'll catch you on the next explainer.